Hello, folks, and welcome back, one and all. Let's see what we can do. Today, we are going to be talking about continuity. And so, let's see what we can do about getting started on this. First thing I need to look at is going to be what is your definition of continuity? And so, I'm going to describe it like this. Again, this is my language. It doesn't have to be your language, but it's any function whose graph can be sketched in one continuous motion without lifting up your pencil is going to be a continuous function. So in other words, I could say that something like this would be a continuous function. Okay. On the other hand, I could do something where it's got like a nasty curve and a jump to it. Something like that is a continuous function. But the minute I end up having to pick up my pen or my pencil to do something like that, I'm going to end up saying that it is not a continuous function. Now, formally, what we say is the function is continuous at a point A if the limit as x approaches A is equal to f of A. In other words, describing it a little bit differently, if I've got an axis here and I want to come up with a graph. So my limit of my from the left does this, and my limit from the right does that. And then if my actual value of my point comes in there, guess what? We're going to say it's a continuous function. All right, nothing terribly exciting in that. Next, let's move on. We have three different types of discontinuities that we need to mention. Okay, the first one is called the removable discontinuity. I know many of you had teachers that just called these RDs. You've got an open dot sitting right here. And again, we'll do something where we say, okay, that's my removable discontinuity. It's continuous except for that one point. Okay, then let's move on and say, what about something like this? When you've got a jump discontinuity, that's going to be when it's on one level from the left and a different level from the right. Okay, jump discontinuity. Nothing exciting in that either. All right, let's see. What else do we have? I also can talk about what is called the infinite discontinuity. You'd agree that on this side, it's going to infinity. Whoops. And on the right-hand side, it's going to be going to infinity. So since they're both going to infinity, it makes sense that we would call it an infinite discontinuity because they are not coming together. But the same thing also holds true if one is going to infinity on one side and one is going to negative infinity on another side. Also, though some people always try and argue this, let's say I've got something like that coming in from the left. If from the left I have a continuous function, it goes into that point and it stops there, but on the right-hand side it goes to infinity, we still describe it as an infinite discontinuity. Okay, moving on. So let's see what we've got here. I got two more examples I'd like you to look at. Okay, and we're going to come up with where I have discontinuities, and I want you to identify what types of discontinuities there are. Okay, pausing, letting you think, and reflecting, and let's see what we can do here. I'm going to say that in figure 2.18, I have a discontinuity at x equals 1, and the type of discontinuity it is a jump discontinuity, okay, because it goes from one level to the other. The second type is going to be at x equals 2, and that is going to be a removable discontinuity. Okay, not too much exciting in that. And it's continuous other than those 2 points. Next, I'm going to look at the figure on the right, and there, once again, I've got just a bunch of jump discontinuities. I've got one sitting at -1. I've got one at 0. I've got one at 1. I've got one at 2. I've got 1, 3, 1, 4, etc., etc., etc. Okay, then I want you to look at this and see if you can identify what types of discontinuities are on this figure. Once again, pause it, jot it down, make sure that you got the right answers here. Okay, there we go. And let's do something like this. I'm hoping that people are going to say yes, at x equals 1, I have a removable discontinuity. Okay. I am going to say that at x equals 2, I also have a removable discontinuity. At x equals 3, I have a jump discontinuity. And then finally at x equals 5, I have a infinite discontinuity. Okay. Of course, I'm abbreviating this because, well, I'm writing with the stylus and you couldn't read it if I actually tried to write out all the words. Okay, next up, let's see what we can do next. Here we go. Come on. There we go. Identify all points of discontinuity and describe what they are by type. Now, once again, this is a piecewise function, so for many of you, it wouldn't be a bad idea to try and come up with a sketch of what this looks like. So here we go. Let's try something like this. I'm going to say that, let's take a look at this first one. And we're going to be looking at x squared. But I've got an open dot there because it's strictly less than 0. Okay, and let's see what else I've got. Next up, I'm going to go to in between 0 and 5. So clearly at the x-axis, that's 5 and 0 there. Okay, and because once again, it's the inequality, so I should be okay on that. Let me see what I can do here. I'm going to have an open dot there and an open dot there, and sounds good. And next up, let's take a look at this last function. Now this is going to be one that once again is approaching infinity because 5 minus 5 gets me 0. 1 divided by 0 goes infinite. I guess the question is it going to be positive infinity or negative infinity that things are going to be approaching? Well, since from the right it's going to be like 5.1-ish, so 1 divided by 0.1 is going to be a rather large number, so I'm going to say it's approaching positive infinity from the right. So I'm going to be looking at something that probably does like that. Okay, so what I can say is here at x equals 0, I've got a jump. And at 5, I'm going to say I have an infinite discontinuity. Okay. Hopefully this makes sense, and well, if not, you can shoot me an email and I'll try and get back to you. Now, I do need to mention this. Polynomial expressions are always continuous. That's going to be your x squared, x cubed, x to the fourth, x to the fifth, x to the whatever. All of your polynomial functions are continuous, and we love that about our polynomial functions because it means I can do a lot of calculus with them. And that's why many of our examples end up being polynomial expressions. So then without further ado, I am going to say we're done for the day. So ladies and gentlemen, I would say go ahead and get to work on your exit slips, and I'll see you again real soon.